Yes, that's correct. Okay, so first I'm going to introduce the problem. Okay, that's difficult with the micro. So in our work we consider the sets, so this algebraic variety actually, so which is a set of third order tensors of bounded tensor train rank, which we write as follows. And then the tangent cone to this variety is defined as a set of all tangent vectors at the current point x. Okay, to the current point x. And tangent cones play an important role in constraint optimization, for example, to find admissible search directions and to define optimality conditions. In these optimization problems on the variety, we need a projection of an Euclidean tensor to the tangent cone, and such a projection is defined as follows. So it minimizes the Euclidean distance from the tangent cone to the Euclidean tensor. The problem, however, is that the tangent cone that we consider is highly non-convex and non-linear. That is why we propose. The projection is also not known from the literature. That is why we propose an approximate projection, which is, as the true projection, a set-valued mapping from the space of real tensors to the tangent cone, but which, more importantly, satisfies an angle condition. So this angle condition is written as follows. It may seem a little bit abstract at first, but further in the presentation, the intuition behind it will become more clear. So the angle condition ensures that the inner product between the projected tensor and the approximation is always larger than a fraction of the norm of the true projection times the norm of the approximation. And this for all projected tensors, and also for all values in the image of the projections. So as I already said, an approximate projection enables to compute gradient-related directions in the tangent cone, which is important for constraint optimization problems. So this is needed, for example, in applications where we want to minimize a continuously differentiable function on the variety. For an example application is tensor completion. The best known approximate projection in the literature satisfies a value of omega like this. So yeah, I've maybe forgot to mention. So in the approximate projection, omega is a value between 0 and 1, and we want to obtain a value of omega as high as possible. So the higher the value of omega, the better the approximation, and when the approximation equals a true projection, omega equals 1. So, and in our work, we propose an approximate projection which satisfies the following value for omega. And as can already be seen, for all problem parameters, this value is higher than this one. And I will conclude the presentation with a numerical experiment where I also show that this also holds in practice. So this is quickly the outline of the presentation. So after this short introduction, I'm going to give the preliminaries to understand the proposed methods. Then the proposed method follows, and I conclude with a numerical experiment. So yeah, what is actually a tensor train decomposition? I have not yet explained that. So for a third order tensor, the first and the last vector of a tensor train decomposition are matrices, usually of low rank, so rectangular matrices, and the middle vector is a third order tensor. So this, I get this question a lot. What is the difference with, for example, the Tucker decomposition or the CPD decomposition? So compared to a CPD or a canonical polyadic decomposition, we need more parameters to define a tensor. But as I will explain, it is easier to to obtain a tensor train decomposition than a CPD, for which we have to optimize a nonlinear optimization problem. And compared to the Tucker decomposition, there would be another factor here, for example, to multiply in the other dimension. So in formulas, this looks like this. A tensor train decomposition is written as x1 times x2 times x3. And the minimal R1 and R2 for which such a tensor train decomposition exists is called the T rank of this tensor. And such a minimal rank decomposition can easily be obtained using simple SVDs. So that is the advantage. You don't have to solve a difficult optimization problem. And the rank can also easily be obtained by the combined matrix rank of the left and the right unfolding of the tensor, which is defined as follows. So it's just a reshape operation on the tensor. We also use a notation of the Stiefel manifold to denote a set of orthogonal matrices. This is important in the approximate projection, as the parameterization of the tangent cone is not unique. So we define orthogonality conditions to improve the stability, for example, of our algorithm. When we have the notation of the Stiefel manifolds, we can also say that a tensor is left orthogonal or right orthogonal if the left or right orthogonal respectively is an element of the following Stiefel manifolds. And we use this notation, so P underscore U, to denote the projection matrices onto the range of the orthogonal matrix U. So this will also be important in our proposed method. So indeed, the tensor train decomposition, as I said, is not unique. For example, we use the following two different decompositions in the rest of the presentation, where the double primes mean that the vectors are left orthogonal, and the one prime, these are right orthogonal tensors. The tangent cone was parameterized by Benjamin Kuchan into the following block tensor train decomposition. So I have no 3D figure for this, but you have to imagine that for this vector there is also a dimension that goes into the slides. So the parameters are U1, W1, U2, W2, Z2, V2, W3, and V3. So these are a lot of parameters. Again, this parameterization is not unique. In the paper of Kuchan, certain orthogonality conditions were defined, but we modified these orthogonality conditions to make the proposed method more stable. And so we use the following conditions. Because of these orthogonality conditions, if we expand this block tensor train decomposition, we get a sum of 6 mutually orthogonal tensor train decompositions. So each tensor train decomposition is orthogonal to the other one with respect to the standard inner product of the vectorizations of the tensors. And consequently, we can rewrite the parameters that only appear once in the parameterization in function of the other parameters, the tangent tensor actually itself, and the vectors of x. Before I can explain the proposed method, I first rewrite the original definition of the projection as another constraint optimization problem. And in doing so, we use the property that the tangent cone is a closed cone for this variety. So this means that this standard product, which also holds for Euclidean spaces, is true. So, and when we insert this actually in this cost function, let's say, we can rewrite it as follows, where this additional constraint is included. and we can even rewrite it in this form. And as you can see, there is already a lot more similarity with the angle condition. So indeed, the true projection maximizes this inner product, and so also maximizes the value of omega that I showed in the introduction. Now I arrive at the main part of the presentation. First, in our paper, actually, we derived the following proposition where we write the parameters of y hat, where we suppose that y hat is in the image of the exact projection. We don't know the exact projection, but still we can say that these are the parameters that appear only once in the parameterization, assuming that we know U1 and V3. And furthermore, if we construct a tangent vector using these equations, so this tangent vector is a feasible point of the constraint optimization problem for any U1 and V3. So we also, of course, we are going to use these equations further in the method. So then is the question, how do we obtain U1 and V3? So these are more difficult parameters, let's say, and we do this with a numerical iterative optimization method, which is based on the alternating least squares method, which is a well-known optimization method that always fixes all parameters except one and then optimizes the problem for this one parameter and does this iteratively. As you can see, we also have two parts in the iterative algorithm. This is to actually to obtain this maximum of these two values. So depending on the parameters of the problem, one of these two parts is going to be executed. And then we have an inner loop with a stopping criterion and certain maximal number of iterations that can be chosen, and also a tolerance on this is actually the norm or the current approximation that we have obtained. So if the difference converges to a value lower than the given epsilon, then the algorithm also stops. And to optimize U1 and V3, we use a truncated singular value decomposition. So this is a standard known algorithm. It's also not very difficult or very expensive in general. Okay. So using this method, and with the parameters defined in the proposition, we show in the paper that we indeed obtain the following angle condition with the following value for omega. I have a few notes on the numerical stability and complexity, but it's not maybe too important, but I will go quickly over it. So we have implemented a method in MATLAB, and for the truncated SVD, we use the SVD function with eikonflag. This truncated SVD is also the most expensive operation of the algorithm. And more specifically, the most expensive step is the first step of the first iteration, where we have to compute this number of singular vectors and singular values of a matrix of this or this size. And in the subsequent steps, we can use, we can simplify this dimension to this dimension. And in general, the sum of S1 plus R1 is much smaller than the dimension of the first dimension of the tensor, and this also holds for S2 and R2. And the stability, we didn't have time and space to thoroughly investigate the stability, but because of the modified orthogonality conditions, we don't use any pseudo-inverse, for example, to project onto the vector spaces. So this is certainly an improvement compared to the approximate projection that already existed. So I want to conclude with a numerical experiment. For this experiment, we generated 50 pairs of random low-rank tensor X and a full dense random tensor Y. Yeah, using the rand-n built-in MATLAB function to generate pseudo-random normally distributed numbers. And we chose K1 and K2 equal to 3. And then we compared the value of this normalized inner product. We use this inner product because we don't know what the exact projection is. And because of the norm of a projected tensor is always smaller than the norm of the original tensor, this can be used as an upper bound on the value for omega and a lower bound on the value of the original angle condition. And yeah, we compared our method with the method from Kuchan, and also we used the built-in MATLAB solver fmincon to the constraints optimization problem as a benchmark. And our code is also publicly available. And then we obtain this figure. So in the left subfigure, the box plots of the data is shown for the three methods. And for our method, we use two values of the maximum number of iterations. This is 1 and 5. And as you can see, for both number of iterations, the normalized inner product is very close to that of fmincon. Which was the benchmark and always larger than the one from Kuchan. In the middle subfigure, 10 individual pairs are shown. And again, the proposed method is very close to the benchmark, sometimes a bit higher, sometimes a bit lower, but this can be explained by the fact that both methods are not guaranteed to converge to a global minimum, only to a local one. And then in the last subfigure, the evolution of eta is shown as a difference. And as can be seen, there is quite fast linear convergence to machine precision. Okay, thank you. This was the presentation.
Thank you very much. Are there any questions?
So I have a general question about tensor train. So I know this is very popular in numerical solution to physics problems.
Okay.
Are you aware whether this has been used in statistics? What's the statistical interpretation of the tensor train?
I'm not aware of a statistical implementation. I'm sorry. Unfortunately.
Thanks. Any other questions? Maybe I have a question. So, like you mentioned that the decomposition in tensor train tensors is an algebraic variety. Do you know like the equations of the variety, or is this too difficult? What do you know about this variety? I mean, you parameterized it, but do you know more?
Yeah, I don't know it by heart, but
I think you have consecutive flattenings of low rank.
Yeah, indeed.
Mateusz Michalek has a nice paper where he solved some Hackbush problems. So I think the equations are known.
Yeah, indeed. Nice. It's so it is known, for example, that if you fix the rank, that it is a smooth manifold. And yeah, I think it's just something like you fix the determinant to a fixed value, for example. And then it is also shown that so if you have a bound, then this is just the sum of all the lower smooth manifolds, and this set of smooth manifolds is the variety.
Okay, thank you. I'll look into it. Thanks. Okay, any other questions? Then let's thank the speaker again. Thank you very much.